It's totally washed out on here. That's not the end of the world. Oh, that's more washed out. Yeah. That looks pretty good. Yeah. Okay, there is a stand-up interactive out in the meadow in about 20 minutes. So hang on. We'll try and keep this as interactive as possible. I just recorded, yep. And we're going to start with some brain teasers. Okay, so polarization in the sense that we think about it, at least in ocean optics, is it's largely about scattering. Polarization comes from scattering events. So we're going to start with some refreshers on scattering as we dive in. Okay, why is the sky blue?
Scattering.
Rayleigh, what does Rayleigh say? Particles are small. It's air molecules. What's the relationship?
Steep spectral sulfur backscatter. Yes.
For scattering? Yeah, so scattering efficiency changes by 1 over wavelength to the 4th. So there's a dramatic increase in scattering as we move to the blue. So we're in this section, if you remember the me lecture from a couple days ago, we're in this section of the curve of scattering efficiency. And air molecules are, tiny, 0.0005 microns-ish. Okay, so why isn't the sky violet?
Maybe just we can see it.
Ish.
Was it the function?
For all these brain teasers, ignore absorption. And that's not why. That's not why at all. Yeah, that's part of it.
Why the gradient like a color we can see instead?
Purple is not a color we can see, but we can see violet-ish. You're right. Our eyes are a little less sensitive to it. These are all good pieces of it, actually.
Is it that the sun's peak radiation is closer to the moon?
Okay, you've hit all of them. So part of it is that terrestrial sunlight, and this is sort of an average plot, right? We know that this changes. You just showed that the clear sky model didn't match your measurements, and I don't think that was due to instrument issues. That's probably due to the different atmospheric conditions. But part of it is that the peak output is more in this area, at least the peak output that makes it down to the Earth. But you didn't hit the one trick of the question, is that actually often it is violet in very rare places. And your point about eye sensitivity was true. So the problem is that this is the human eye spectral response function integrated across the 3 bands that we see. And sometimes, like in a sort of hazy, more normal environment, we get this where it's peaking in the blue and it looks blue to us. But if you go up to the top of Mount Low, and if you could see it a little bit better, the whole sky would be violet. But that was really nice. You guys got all the different pieces of that. So moving on to the second component of this, why are sunsets red? Path length, right. It has very little to do with absorption, although that does add to the dramaticness of many really nice sunsets. But when all the blue light is scattered out from where you see it, we're looking at a very long path length through the atmosphere. Okay, so a question for you that might be a little less intuitive. When might red scatter more than blue? And the answer is in this plot. Part of it, but not all bigger. Where would we be on this plot that red scattering more than blue? On the troughs, but almost. Somebody shouted out. Okay, there's only one more part left. What's the other part? We know we're not here. This is where This is where blue is increasing. Remember the size parameter. Size parameter is radius over wavelength. So let's say we have a fixed particle size. Let's say our particle is 1 micron. What's going to make this relative parameter move a little bit? A change in wavelength. So if we're here, the reason that this goes up is because our x is actually increasing here a little bit for a given particle size. When your wavelength on the bottom of the fraction is smaller, when it's bluer, you're going to move up. When it's redder, we're going to move here. So if we're here on the decline, when your wavelength is red, it's going to scatter a little more, and blue, it's going to scatter a little less. And this is only for an atmosphere or a monodisperse particle size distribution. These are for particles that are basically the same size. But for the atmosphere, that's an okay assumption sometimes on a clear atmosphere. And this is basically just accentuating that same thing. So as we're here, blue's scattering more efficiently. And as we're here, so that Rayleigh regime breaks down once the particle size is near the same size as the wavelength. We actually get these really weird conditions where red scatters more. Can anybody think about a situation where we might be in that part of this regime in the natural environment? What do you need for a red sky and a blue sunset? Where might that happen? Yeah, that's true. Do you think that ever happens? Yeah, what happens during the apocalypse?
No.
Yes, we can get this during volcanic eruptions. But on Mars, every day, most of the particles in the atmosphere are the right size where there's a blue sunset and red sky. Pretty cool. Yeah, and also just volcanic eruptions and certain fire conditions, you need the specific particle size. So it has to be fairly monodisperse. If you get a polydisperse, large, broad particle size distribution, it would cancel out those weird oscillations, but you have to be right in the right part of that scattering efficiency. And this is just a plot for you to reference when you're looking at this later. You have a right here. And so you're typically in the range from like 0.5 to 1.2 microns for visible light for us to be in that weird increased red scattering regime. Okay, so for a quick intuition check, how can we get red sky with particles that are really small? Let's say we're in Rayleigh. How could you look up and see a red sky? You've already answered this kind of, but just twist it a bit in your brain.
Is that just the longer path length?
Right,
Talking about?
right, basically. But if your atmosphere was really dense, like it is on some other planets, just Rayleigh scattering would be enough. So if the atmosphere was 20 times thicker, or 10 or 40 times thicker, we would actually see red everywhere we looked. And again, that's just because all the blue light will have been scattered back out. You guys feel okay about those? Okay. We'll move on to the meat of the presentation. And this quote, I love this book. I have it in the library that we brought. As with radiometry, polarization can be a confusing topic. Unfortunately, unlike radiometry, complexity is not primarily due to confusing units. And just as sort of a refresher, I'm going to do sort of an aside at the end if we have time on what is light, based on some talks with Kurt last week after your confusion on if Rayleigh scattering includes absorption. But mostly for now, keep the mental model that light is a wave. It's just going to be a little bit easier to work through some of the discussion that we have. Kurt also had an add-on. He said, you can think of individual photons as having polarization and work from there, but believe me, you don't want to. So the brief structure of what we're going to go through is first, sort of why do you care? Why should we care about polarization in ocean optics? The follow-on is what is polarization? How do we describe it? And then the third section will be how do we measure it? How do we measure it practically? How are we going to measure it this afternoon? So first, we mostly care because if you guys saw Avatar, The only reason you could see it in 3D was because they actually project it in two different circular polarizations, and then each of your glasses are a different circular polarizing filter. So this is primarily why we care. But why else do we care? Really, at least in the questions I'm interested in, and sort of as we move the field forward, polarization can tell us a lot about intrinsic particle properties. So it can tell us about size, morphology, composition via the refractive index. And maybe we can certainly measure this in situ and learn a lot, and sort of we're working towards measuring this remotely, and this has been done in a few limited examples. Okay, the next few slides will be kind of painful, but there's only, I think, 4 painful slides, and then we'll be on to some more fun. What is a dielectric? Does anybody know what a dielectric is? Just a simple explanation of it.
I don't know if I can give a simple, but you should have like 2 plates with some medium in between, and that medium has a permittivity.
True, that's sort of a classic, but water's a dielectric, and air's can be sort of a dielectric.
And so I guess there's some charge separation.
Yes, exactly. There's charge separation. And really it's a material that doesn't easily allow the flow of an electric charge. It resists the electric field a little bit. Polarizability, we've discussed a bit in the absorption lectures, and it's this tendency of, I'll show some plots on this, but it's tendency of matter to acquire something of a dipole. And actually this property of how it acquires that dipole and its resistance to the electric field is largely what determines refractive index. So you can think of as light moving through some medium, the way it interacts with the electron clouds there, and as it sort of resists it, that's what slows down the speed of light. And refractive index is just simply the speed of light relative to the vacuum. And then permittivity is sort of the follow-on to that. It's how polarized the dielectric gets given an electric field. Okay, let's take a step back and think about resonance, because a lot of the things sort of the mental models that I want you to have as we think about scattering and polarization are about resonance of the wavelength of light with some medium. The classic example, when you're in the bathtub and you like squish the water and you swish it and you swish it and you find that frequency that is perfect for getting the biggest wave, like that's the resonant frequency in that tub. The reason the tides are so extreme in Maine, and as we get further north up into the Bay of Fundy, is because the geometry and bathymetry of the Bay of Fundy are a better match for the natural frequency of Earth's tides. So that's why it is extreme, because you're closer to that resonant frequency. You can imagine when you're pushing somebody on a swing or you're kicking legs on a swing, you're actually timing the kick of your legs with the resonant frequency of that pendulum to better increase your amplitude. And those weird oscillations we see in me can be thought of as the wavelength or the frequency of light better matching the resonant frequency of that medium or that dipole. Yeah. Questions on this? Thanks. And this is sort of, you can imagine that harmonic input from light, from the electromagnetic wave. Here you can see as we're reaching closer and closer and closer. And then you can imagine if you're pushing somebody on a swing, this fast, like they're not actually going to gain any amplitude. So that's sort of where we go once we start to move too fast. And again, this is sort of a mental model I want you to have. It's not necessarily an exact description of, certainly not of the like QED that's describing this. And interestingly, the resonant vibrational frequency of CO2 is really close to the thermal infrared that the Earth emits. And that's why we have the greenhouse effect, because it really well matches that vibrational frequency, as Meg discussed in her absorption lecture. Okay, this is just sort of, I wanted to show a schematic for permittivity or polarizability. I'm actually kind of resisting from calling it polarizability because that's not what I mean when we talk about the polarization of light. I mean, that means like the alignment of these polar molecules. We're mostly going to refer to it as permittivity here, but Again, you can imagine there's just a bunch of water molecules, or some, the different dipoles that represent some particle. The refractive index sort of depends on the relationship between this input light field and how well they align and how well it resists that input. And I think I told you, we went over this in the me lecture as well, but this is refractive index. It's just simply the speed of light in vacuum over the speed of light in your medium. And that's literally just defined by the electric permittivity. So the magnetic permeability, at least in air and water, is almost the same as it is in vacuum. So these basically just cancel out. And so really primarily in the things we're concerned with, this is what's determining refractive index, and thus what's determining scattering. The only reason I'm going into this sort of depth is I want you to think about that refractive index is going to change these dipole resonances. It's going to change how it interacts with light. It's going to change our scattering efficiency. And it's going to change how it polarizes the light that's scattered, what we're measuring. So we're not really going to worry about this too much. So if this is sort of what you're thinking, it's no problem. But fundamentally, this is sort of part of what's determining the refractive index, and it's why we can use refractive index as an indicator of composition of particles. And polarization can give us some indications of refractive index. Okay. So the big takeaways there are that EM waves make dipoles wiggle. When they wiggle, they radiate. Everything's wiggling unless it's at 0 Kelvin. And the way they radiate depends on that incident polarization. And in general, these are just heuristics to have. The higher the refractive index compared to water, let's say, the more mineral your material is. This is sort of our general, if you only get sort of a relative refractive index, the higher it is, the more mineral, the lower, the more organic. And most organic things are mostly full of water, so it makes sense that they're pretty close to water. Yep.
Are you talking about like above 1 and below 1, or are you talking more?
Typically not really getting below 1 unless we're hitting bubbles and things, but I mean, like a phytoplankton might be from 0.05 or even 0.02 to 1.1. Sorry, from 1.02 to 1.1 or higher with coccolithophoros and things, and minerals maybe 1.15 and up. Reasonable ranges. I'm getting lots of thumbs up from the back row. Okay, so Wayne went over this actually in a really nice review, but what even is polarization? What parameters could we use to define this wave? Let's say 3 or 4. If we were to have 3 or 4 variables describing this wave, what would they be?
Amplitude or 2.
Amplitude, exactly. Yeah, amplitude. But direction, exactly.
Frequency.
Yeah, frequency or wavelength. And then the last one is the polarization. So let's ignore the magnetic field, and let's just look at the electric field. And the way it's, so here, we might say it's vertically linearly polarized compared to this reference plane here. And that's all we're trying to describe with the polarization. And it's called polarization because, if you think of a wave that's coming to you, this is the degree on the polar axis. That's the only reason, it's called polarization. Okay, so why is scattered light often polarized? And here we're just thinking of Rayleigh. We're just thinking of simple, tiny particles compared to the wavelength of light. Check out this video after the class. This is a really nice overview.
Considering the interaction with the electric field.
Yeah.
So there is a rotation due to magnetic.
Well, the simplest idea I want you to have when you're thinking about, the Rayleigh approximation and scattering by really small particles is that when I have these kind of lined up. So when a dipole is oscillating vertically in this plane, it's not actually radiating at all in the axis of oscillation. So you can think of this is sort of the way if light hits this particle and it's tiny, it starts oscillating like this. It's going to radiate in sort of a cloud like this with a probability like that. So that by itself will polarize the light, because you can imagine if you're looking from this direction, a lot of what you see here by small particles will have been polarized like this, and none of it is going to scatter this way or this way. So a lot more of it is going to then scatter this way. And if that doesn't make sense, we're going to go outside right now and do this with a polarized piece of rope. And I want to do this in about 5 minutes total. So let's go. Oh, we're gonna, yeah. Oh, I think he's notes. Our downfall. Right? We're gonna set it halfway. So after that, hold it. What's happening here is the way it's polarized something. It is cycle polarized. Number is not. Let's if you'll try and do it downward. So what's happening is there's no polarization, there's no scattering as the light is oscillating from frequency. Enough long, so almost so it's not like it's an exact analogy, but I want to have this in mind as we're thinking about scattering coming in like this. Got a hit a dipole, it's going to scatter out like this. But scattering like this, through up with like never knows the ritual. It's really sort of for thinking about this, we're thinking about 1096. If we were to have other ropes out here, it works quite well. It does start to transfer. Just like what if you remember, they want to let the light go right at 90 degrees, so kind of when you're polarizer on, start to see a lot more light. And we'll restate that now. So a really good point. So yes, it's not negative polarization. Actually, homogeneous spheres don't change. They don't change in polarization. Any spheres don't change. It's that channelization that's filter. It's preferring to scattering light like this, so it looks like this. The light now is polar. But if you look at the other angle, that's where the other light's going. That's where the light like this is rated. So it's not really that there's no magical polarization. That preferential scatter different clouds based on altitude. And so basically, yeah, I mean, that's what the sun's sun's here. What 90 degrees, highly polar. Closer, one further away. And then, and these are basically sort of the Gaussian. So the input polarization is then aligning the dipole to oscillate. Well, they're randomly that first, and then the input field has to be aligned. Right. I mean, let's say it's not polarized like the sun, lots of all different types of. That's question. I mean, you can say I kind of know it now. And then I look up people who still have and try to keep the head on straight. I have to be the same to the measurement connection. Like, go out to the right world. But then your head on straight and keep your down to the right and nothing to the right and right. So if you can imagine, you don't expect that to go. I mean, here again, it's just analogy, but if there were, both connected this way, that would oscillate that way. So now this is both of the field sort of. In this, I mean, this don't say we talked about. Okay. What time is it? It is 11 hour. Fantastic. Okay.
Rush over.
Something.
I think actually.
Everything else. Okay, that was your break, so we're gonna jump right back in.
So was that from a text, that example from a textbook or something?
Yes, this is this fantastic Shercliffe polarized light 1968 or 69 that we have in the yeah. Okay. This is just actually describing exactly what we were talking about in context of mostly light in the atmosphere. So you can imagine the sun comes in, or some molecule, and again, we're kind of thinking, light's coming in on this plane, it's unpolarized, but you're looking from down here up. So the light you see down at 90 degrees to the solar beam is going to be highly polarized. If you look at an angle here, it's going to be just partially polarized. But if you were looking straight at the sun, it would be unpolarized. There wouldn't have been any like filtering event to change the dominant polarization. Okay, so what happens if we have multiple scattering? Let's say you're, in a dense atmosphere, or you're just in 5 or 10 meters of water. There have been multiple scattering events. What do you think is going to happen? Yeah, so typically there are many events changing the polarization of light with different orientations, and that ends up sort of depolarizing or even leading to a nearly complete unpolarization of the light. Yeah, exactly. And so in our measurements today, particularly in the horizon, we'll try to make sure, we're not too concentrated of a solution, because we really only want one scattering event. Okay. Craig Bourne has these. You guys need to read these books: Fundamentals of Atmospheric Radiation, and just the fun books. clouds in a glass of beer. There are many good quotes. And this one I think well portrays both the complexity and the benefit, which is that all the simple rules about polarization that we just described for small particles are broken when we turn from molecules and small particles to particles comparable to the wavelength. And this is just showing, this is actually some neat results of particles of different sizes. And so you can think of this nice little degree of, this is the degree of polarization. And here, this is small particles, and there's just this nice Gaussian across scattering angle. This is for green light in this plot. This is from that atmospheric optics set. You can get really weird stuff when you have particles that are around the same size as your wavelength. And again, this is mostly for monodisperse PSDs. Okay. In the atmosphere, of course, it's rarely, well, today actually it was pretty blue, but like yesterday, we're actually having lots of aerosols, which are a lot larger. And so depending on where you're looking, it may be a mixture of the Rayleigh approximation, so highly polarized, depending on your geometry, but also lots of knee scattering. And that's a lot harder to predict exactly how it's gonna polarize the light. And in the ocean, we're almost never, it's almost never pure water or pure salt water, so we get lots of polarization impacts. Okay, how do we describe this mathematically? Do you remember the name of the tool we use from Wayne's lectures? So Stokes vector and how do we transform the Stokes vector? The Mueller matrix. And you'll see this in text called the scattering matrix also. I wanted to remind this because when I first heard this, I kind of forgot exactly how to multiply a vector by a matrix. So you guys know what this will add up to and what this process is? So when you multiply a vector by a matrix, you need the number of elements in the vector match the number of columns in the matrix, and you multiply this by all these, this by all these, this by all these, this by all these, and you add them up. So what's that going to add up to for us? These are what we're going to, and 4. So that's the whole math. That's all you got to do. The hard part is measuring the Stokes vectors and measuring the Mueller matrix. But if you have those, you can predict this transformation quite well. And this is a nice slide from Mike Twardowski. So this is just that, but I'm just telling you what's in the vector and what's in the matrix now. So the first element of the vector of the Stokes vector, which Wayne already went over, is the total intensity of light. This is the vertical or horizontal polarization, the 45-degree left and right, and the circular polarization. And then the output, so that's the incident. It's transformed by the Mueller matrix and a factor here. And then we get the scattered beam. And so let's think about some super simple examples. Let's think about Rayleigh scattering at 90 degrees. So let's just say it's unpolarized light. That's just 1 and 3 zeros. Rayleigh scattering here. This is basically just the VSF. This is the volume scattering function, element 1, of the Mueller matrix. I think was in that slide just to, yeah. So S11 is just the VSF. And this is the change in vertical, and this is the change in linear polarization. And so as we do that, we're just multiplying these by each other. We go here and we get light that's perfectly polarized vertically. So these only go from -1 to 1. And all of this means is that the intensity didn't change. And we've normalized it to intensity. So let's just say intensity didn't change. And the light's all vertically polarized when we're looking 90 degrees after a Rayleigh scattering event. And I'll put these slides up this afternoon if you want to go over them. Let's think about a linear polarizer that only allows horizontal transmission. So we'll have some of these in the lab today. This is the transformation that you're putting light through when you put it in. And here I'm saying we're inputting linear polarized light that's completely horizontally polarized. What do you think that's going to do to the output? You can either add it up or just think about what horizontal light going through a horizontal polarizer will do. It's going to be exactly the same.
With a little heart.
Well, we're losing some intensity through the polarized. I'm actually ignoring the factors here, but many of these will have sort of a factor of, because I'm normalized by the VSF here.
Okay.
And most of the time when you see Mueller matrices in, not always, but in text, they'll often normalize by S11 just to show you so you can see the shapes here. So this is linearly polarized light going through a vertical filter. What's going to happen here? This is assuming a perfect filter, but yes, it's going to become 0. And this, I just pulled these values from Ken Voss and Ed Fry's sort of famous paper on measuring the Mueller matrix across many angles in the Atlantic and the Pacific. So this is the average Mueller matrix for the Atlantic Ocean. And here, what do you think this is going to do to the light? We're inputting unpolarized light. What's that? Yeah.
Polarize it.
Yeah, it's going to polarize it. So after this scattering event, water leaving the Atlantic is pretty highly polarized. And again, I don't know these exact locations. They were sort of central Atlantic. So this is, pretty small particles. Most of the scattering is dominated by water. So you can imagine, this is the sum total of all that. And just so you sort of have this in mind, what I'm showing here in these simplified schematics is just for 90 degrees. Actually, a lot of the work goes into, so this is that same matrix. These are those same 4x4 elements, but here we've normalized it to S11. So this is just 1. That's why they're not showing anything there. And, I just actually grabbed the values at 90 degrees for each of these. And for most of this, it's 1. So actually we get to ignore a lot of makes the math even easier. But you can see here, this is the element for the linear polarization of light during a scattering event. And you can see here, it sort of goes back to 1 or to 0, which means as we're scattering in far forward and far backward angles, there's minimal or no polarization. Sure, Trev?
You just go on the last one, the matrix first times a vector.
Yep, sure. So here, it's just 1 times this column, which gives us this, and then 0 times all the rest. So our final product is actually just this.
Okay, I was.
Yeah. Yeah, I should have put an X through it. But that's because we're putting in unpolarized light. If we had put in light that was slightly polarized, we would be using those other factors. Okay. So water leaving the Atlantic is fairly polarized. Okay. Go ahead. You have a question?
I think this will
Okay.
cover it.
Why do we care? If you're willing to deal with some of this complexity, if you're willing to spend, days and weeks and months sort of thinking about that geometry and thinking about hypotheses and expectations and how to do this sort of Mueller calculus, we think we can learn a lot about size, morphology, and composition of particles in the water. That's our big bonus at the end of this. And while we probably will have to come up with inversions, if we could measure this, and certainly when we measure it in the lab, these are direct impacts from intrinsic particle properties, as opposed to trying to infer many intrinsic properties from extrinsic. So when I say intrinsic, I mean properties of a single particle. And when I say extrinsic, I mean concentration and bulk particle properties. Okay, so where in this range are the particles in the water, ignoring water molecules itself, going to polarize predictably? We've said this a couple times, just sort of making sure, checking back to the start now that we've gone a little bit deeper into the complexity. Yeah. So sort of the colloids, the bottom end of colloids, and I mean most of these sort of range are still going to be fairly predictable, although deviations from what we expect from Rayleigh might be interesting to us. Megan and I have run some 30 and 60 nanometer beads and some small colloidal particles, and the beads match really well, but some of the smaller particles aren't exactly what we would expect from me, and that's different because of the different refractive index, or because of inhomogeneity in the particle itself. And as we go up here, well, it becomes a lot weirder, but maybe there's a lot we can learn if we can learn relationships between those particles and these scattered VSF and DLP properties. Okay, I think I had it on a slide, but I maybe didn't actually define the degree of linear polarization. So let me just go back to that. So when I say the degree of linear polarization, which is often what people are deriving, and that in combination with these elements and the VSF are quite informative. It's just the ratio of these two. It's just S12 over S11. And that's basically normalizing the change in linear polarization by the intensity. And that just gives us a value between -1 and 1. Yep.
Just not use what some people also refer to the degree of polarization of this, the beam itself at the Q.
True.
So it's not always.
Yeah.
We're talking about the intrinsic degree.
Yeah. But that's a good point. And actually, you may, if you're talking to atmospheric folks or other folks, you may that's exact. I had actually confusion on a call for that exact reason.
Yeah. Yeah, you and you over high.
Yep.
Which is, it's linked to the 1-2.
Right.
For the case of unpolarized light.
Right. That's a really good point. Go ahead. Sorry, Olivia.
Could you repeat what you just said? I just wanted.
Sure.
Yeah.
So when I'm in the lab today, when we're talking about degree of linear polarization, we're actually talking about the ratio of this over this. And actually here that ratio has already been taken. So what we're seeing here is the degree of linear polarization. And how I want you to think about that is, let me go back to this slide. So it's this divide. So think of this, this is the incident light and this is the scattered light, but this is the transformation of it. And the transformation is what's telling us about the particle properties. The incident light doesn't tell us anything. By measuring the scattered light, we can learn maybe what this transformation was. And it's transformed by the particle properties. And so what we're looking at here is, this is basically just the amount that the light is polarized during the scattering event. And this is the total intensity of scattering. So you can almost think of it like, this analogy may be confusing, but we look at the phase function of scattering, which is VSF normalized by total scattering, because then we can kind of compare shapes quite well. And so here what we're looking at, we're taking out the total amount of light scattered. We're normalizing by the total amount of light scattered. And we're just looking at how much the light is linearly polarized by a scattering event. Do you have anything to add to that? Go ahead. Daniel, were you going to jump in? No?
Yeah, no, that's good. It's just that often the S1 is the phase function.
It is, yes.
And then the VSF is the 1/k² R squared.
Yes, it's true. Right, so you're normalizing basically by the phase function per angle. So then you get this sort of shape. And this is telling you, okay, it's highly linearly polarized vertically at 90 degrees. And then it's sort of decreasing as you move to here. And I'll show you some measurements of shapes of this. Maybe that'll help a little bit, but we can definitely talk about it more.
So you had said that multiple scattering leads to depolarization, but then for the ocean example, we said that light is coming out fairly highly polarized. Mm-hmm. So is that indicating that multiple scattering is not occurring, or that there is a final polarization?
Well, think about the single scattering approximation that we're using, that we discussed in the rate of transfer lecture and others. You can often model RRS quite well just by BB over A. And that BB is, we're assuming, a single scattering. I mean, most light that comes out has been scattered once. And that's not true for all conditions, but do you agree with that? Yeah. Contact, go ahead.
There's usually some more.
Yeah, right, definitely. Yeah.
I think these pathways, there's always.
Yeah. Right, absolutely. And this is just some knee results from Loisel. And here you can see, actually, what I kind of want you to take of this, the number on the line here is the degree of linear polarization. And what you can see is that you can still be fairly big and have a high degree of linear polarization if you have a very low refractive index, if you're very organic. And you might be kind of small. This is just the particle size distribution parameter. This is gamma, or the Young slope that we've discussed. So just think of this as stuff's getting bigger as this gets flatter. This is just the relationship between these two parameters. I think we have some papers on the drive that try to get at this from ACS measurements and BB over B measurements. It just sort of provides some intuition for what we see when we're doing these measurements. Okay, so we have been talking mostly about scattering, but I just want to point out that absorption can also filter polarized light. And here, I'll just kind of describe what's happening in the filters that we're using, and also to kind of, for many folks, you see actually many of the lab demos are like light going through a fence pole and allowing one polarization through. But for most filters that we're working with, it's actually the opposite, where there are all these long molecules sort of sprung out here. And when light comes through perpendicular to that, it mostly allows the light through because it doesn't allow for this long interaction with this long molecule to allow it to be absorbed. And so we can absolutely either scatter back, reflect back a certain polarization, or we can absorb a certain polarization to create polarized light through some kind of filtering process. Yeah, exactly. You can see here, basically, we're not aligned with the oscillation axis for many of these filters. You made a comment on this last time. Go ahead.
Light demo with the concentrated sugar water.
Mhm.
How are the molecules in that aligned? In that tank full of like glucose or whatever. Have like a tank full of liquid with the molecules that float around it. Are they aligned? No, right? And we were shining in polarized light, and then it was all being, what came out was being rotated just a little bit. So it was like whatever molecules were in there that happened to be aligned with the light coming in, then rotated it coming out.
Okay.
Was sort of related, but I don't know.
Yeah, absolutely.
See that. That's why I'm pretty good.
Yeah. And I want you to think about, some of this is probably new. Maybe some of this is, old physics you haven't thought about in a long time. But for many of these things, if you want to use these techniques, you kind of need to get your head around some of this. But the actual measurements are typically what we've been doing just with polarizing filters in front of either the input light or the detector. And that's hard to do well. It's hard to do without some sort of polarization sensitivity in your instrument in ways you don't want. But the measurement technique isn't really adding that much complexity to the theory of the measurement. And there are lots of ways we can do this. There's this great, Riley Blocker has this super cool work with Ken Voss using Pixpol, which basically in each one of the CCDs in front of his camera, he has these little polarizing filters. And then he puts the sensor out in the water. And you get amazing hemispherical polarization DLP measurements. And well, it kind of gives it away, but where's the sun in this? And why does that agree with your intuition so far? Sorry, you're a fisheye lens looking straight up at about I think this is at like 5 meters in the water column. Yeah, the sun's right here. So the light from near the direct solar beam, other than maybe these little artifacts here, is not very polarized. And as we move towards 90 degrees from that, even underwater, you're still seeing a high degree of polarization. And some interesting outcomes from Riley's work, this is from his ocean optics talk, he sent me these slides, is, this changes spectrally. So the way we're looking at this, there may be some interesting information to gain from this information across different wavelengths. And this is the instrument we're going to use in lab today. This is my lab assistant here. And he was pretty scared by it, actually. And this is, what's that? Thanks. Oh, those are from the class. This is the LIST Horizon. It's a new instrument from Sequoia Scientific. And the measurement approach here is actually the whole front is basically a LIST 200X. And then it has a transmit beam here. It goes through a linear polarizer. So it inputs vertical and horizontally polarized light. And it also has 24 detectors for side scattering, because that's where we see most of this impact of polarization. This is available for projects. We'll be using this afternoon in the lab. And one of the real benefits is it can run in a flow-through mode, so you can get nearly continuous measurements. And the approach there, there's a really nice appendix Wayne added to the lab on this, so to help sort of clarify this when you're thinking about it during the lab. But the input light is filtered and the output's unfiltered. And basically we get these two different parameters, and we're able to either take the ratio of them to get the DLP or subtract the first measurement from the second to get S11 and vice versa to get S12. And some of the data from this is pretty interesting. So these are data we collected. Charlotte was at sea on some of this as well as many others. So this is IFCB imagery, and these are the DLPs that we measured during that same period along with the APs. And you can see there are pretty distinct shapes from an open ocean assemblage, coccolithophores, this nearly monodispersed dinoflagellate bloom, coastal detritus. These all have sort of different shapes, and you can extract parameters where the peak DLP is and the magnitude, and even the variability seems to have some indicators of what's going on for these particles. Mike Twardowski has an instrument that measures this that Wayne discussed, and here you can see he's comparing to that classic Boston Fry paper, and as well as just what we would expect from molecular scattering from seawater. And so we think, and actually in this paper, they go into extracting these different shape parameters and seeing what they connect to. There's a classic paper by Volton et al. That has some lab experiments. Again, I'm including that metric from Boston Fry just for reference. But this is a VSF. And this is the DLP. And what we're showing here is this is microcystis with and without gas vacuoles burst within it. And actually, there's a pretty different shape here. Silt particles, there's a different shape for different size particles. So we know this, we know this is impacted by these particle properties. Go ahead.
Why do you have these gaps in spectra and shoot before?
That's a great question, and it'll come out in detail in lab today. But actually, these do connect, and actually there's overlap here. This is an active research project that I spent a big chunk of my postdoc on. But it seems like at specific angles, we're getting reflection from the lens, and that's a totally different polarization. And it seems like that's disrupting the true DLP measurement, as well as I'll show you the phase function of the SF during the lab, but it's totally disrupting. So I haven't been able to calibrate those specific angles. And this is one of the challenges of sensors that measure polarization is little reflections can dramatically alter your measured polarization state, particularly for small particles. When you input light for the exact reason we discussed in the dipole model, when light is an input polarization like this, it's not really scattering up at all. And so you can imagine it actually asymptotes to basically zero. And you can imagine tiny reflection from a different angle that has like 3 orders more magnitude or 4 orders more magnitude of scattering. If 1% of that light reflects into that detector, it would totally disrupt your measurement. We can go into much more detail there. Go ahead, Daniel.
I really, this is me like such a great example of why this sort of metric is important. So on this slide, you see absorption on the bottom. And in color, we're trying to use small changes in absorption spectra to tell you about the species. So here we have different types of species, dinoflagellate, coccolithophore. You see small changes in absorption, right? But it's not huge changes. But if you look at the degree of polarization on the top, you have huge changes in that shape and that function, or changes in the assemblage. So, it's really as invaluable as absorption spectrum, hyperspectral absorption spectrum would be for unraveling what's in the water.
Right. Particularly because this is involved with the BBP, and it's tough to differentiate those two. Yeah, thanks.
There's like more noise or more lines that don't cloud on top of each other depending on each of these, and I'm wondering why that is, because like the dinoflagellate blooms, which you said was almost homogeneous, has a lot less variability than
Yeah, it's a great point. And actually, I think there's probably information to extract there, but it's also worth noting this is a pretty small sample chamber. and it has mixers in it to keep everything suspended. And so you can see the coastal detritus, and actually these are all, I have the scale stretched, so these are all the same. But there was a ton of scattering in that coastal detritus example, and yet seems to be very little noise in the DLP there. Right, whereas for some of these, it's probably variability in exactly which particles are in front of the beam. It may have to do with morphology and which orientation it's within. And certainly once we're on the lower end of our sensitivity, some of these are from like the central South Atlantic, and there's just not many particles within the sample chamber. And so you can imagine, a little bit of difference in what's in front of the beam is going to change that a lot. Some nice work from Daniel using the list VSF, which we also have here for the month, showing differences in different waters off of scripts. And so here it's both the phase function and the DLP across different angles. And I'm just highlighting some more Daniel's work showing actually dramatically different phase functions and DLPs for different microplastics. So there seems to be some really nice hints that we can differentiate microplastics, and whether or not that signal propagates to remote sensing is a totally open question. But clearly for in situ samples, you can really tell this difference. And I just wanted to suggest this as sort of as we move forward. So this is above water polarimetry measurements, and there's a few groups doing this. And here, you can see different wavelengths. It's a lot. In some ways, it's easier to make this measurement. In some ways, it's harder, just like measuring IOPs versus AOPs. But the shape generally agrees. These are different stations on a transect offshore. And that moves us to sort of where we would love to go with this, where you guys hopefully will bring it. PACE has two polarimeters, SPEX1 and HARP2. And so for HARP2, this is the multispectral angular distribution. This is what are they calling this now? Hyperangular red band. And actually, you probably can't see it. Let me turn off the light real quick. Here I'm showing a single image as you move through these different viewing angles. So you can imagine actually the way that the HARP2 operates is it's flying along with PACE, and it's measuring, at these different angles. And then you have it's a whole challenge to georegister this because they're taken in different moments in time. But you can see glint moving through. And actually, if this is properly stretched, you can see the cloud reflectance changing a fair amount. So you can learn, you're basically probing the VSF with this multi-angle radiometry and multi-angle polarimetry. Yeah. So from there, before we wrap up, I'm going to give a quick intuition test. Is light from the sun polarized? Oh. Is light from the sky polarized? Depends on your viewing angle. And is light from pure water polarized? It depends on your viewing angle. But at 90 degrees, absolutely. And is light from the ocean polarized? Typically, depending on your geometry, there's some polarization signature. We're almost exactly at time. So I just want to give a quick reading list. These are some of the same books I recommended after the me lecture. And I have 2 more slides, but I want to stop for questions first and sort of check stamina.
I think this is my intuition not working out so well on this. Why is 90 degrees the key angle here where the polarization is the strongest?
So the intuition that I have that may or may not represent what's happening between a photon and a particle is the dipole representation that we've discussed. So because light does not radiate in the axis of oscillation, that is what's polar, and that's so you can imagine light's coming in, and 90 degrees is exactly the axis of oscillation. And so at that angle is where it's going to be most highly polarized because it's coming from a different angle of oscillation.
Right.
Yeah.
And that's just because everything is relative to the incoming light. So,
yeah.
It adds something
Absolutely.
better. It also helps it is the most polarized there, but there's actually happens so much light there.
Yeah.
So, you have all this light going in and it's unpolarized. 90 degrees, you have highly linear polarized, but half as much light, you lost half that light. So there's less light.
Yeah, so if we think about our, actual amount of scattering, it's gonna be like this. For, well, something like that, for Rayleigh scattering, right? So there's less light being scattered there. This is from 0 to 180. Right. And again, it's being polarized by this. I think of it as a filtering process. So light is much more highly polarized, but right, there's less of it.
Now looking at like 0 to 180. With the other hemisphere as well, we feel see polarization on both sides, right?
Sorry, say it one more time.
You'd be able to see polarization on both sides of the particle journey. And the drafts below it, right? If you did like a 360 around the front.
You mean like if we spun this around on this axis?
Yeah, if we did like 180 to 360, is there like an additive thing like on the other, like when we're in the rope exercise, you would have polarization coming out of both sides, basically.
Yes, so the geometry that I don't even know how to sketch this, but if you remember Wayne's sort of VSF plots, for here, it's right, it's just 0 to 180 from, the beam being unscattered moving forward to total backscattering. Right, but we think of it as symmetrical if you were to do the other section of it. So that's why we really only think of it as 0 to 180. Because this we think of as a mutual symmetry, either certainly in Rayleigh type scattering, but also in bulk assemblages of randomly oriented particles.
Right.
So yes, this would be the same for the other path. And if you were to spin this into 3D.
So if you double the lines of polarized light coming out at negative degrees, would that be force amount of light coming in as incident? Makes sense.
I think I need you to sketch that. I'm not totally sure what you mean.
So
Yeah, absolutely. Yeah.
So if light is depolarized on the way down due to multiple scattering through the atmosphere, why do we?
No, it's just that light leaving the sun is unpolarized. It's not depolarized to the atmosphere. The atmosphere typically polarizes light, unless it's cloudy and highly, then we get some maybe depolarization of the Rayleigh scattered light.
Right, but I guess the question was gonna be like, if we have a satellite and there's an atmospheric layer and polarization is coming from the ocean, how's that polarization?
Oh, that is extremely challenging I mean, this is part of why this has not been done yet.
Yeah.
Is aerosols in particular. I mean, most of what the reason HARP2 is on there is to extract aerosol atmospheric properties because they dominate the signal. In my mind, we may be able to do this from something like HARP2 if it's super clear, if you only have Rayleigh scattering, and maybe you know really well what the rest of the atmosphere is. But if we're using this data to calculate what's in the atmosphere, the signal left over for the ocean leaving DLP is really challenging to get.
So
Go ahead, Daniel. Yeah, give me the follow-up.
The follow-up was gonna be in yesterday's data set, we had LiDAR, which was aerial, but there was a parallel and a polarized, or a parallel and perpendicular signal component that we extracted. So what's the deal with that?
Well, that's what I was gonna ask if you talked about how LiDAR measures the depolarization. So yeah, there's that too.
Right, it's
extract
right. It's maybe a really useful signal when you know what the outgoing was, and you can, it's a higher signal to noise signal sometimes, and right, there's some interesting work there.
And that's cross polarized. So it's parallel going in and then perpendicular coming out. So it's not this degree of linear polarization. It's actually it's a 2-2 element for me. So that's it's measuring something slightly different.
And I'm gonna save this for the lab, but we have a nice explanation for you for our optical Barber pole, and we're not going to do it again in lab today, but we can do it if anybody wants to do it again, we will. The last thing I want to give before I give Andrew some time is based on these discussions I've had with Kurt actually during the class when I took it as a student, and again still over email. I think I'm asking him the same question, like what's actually going on here. And I'm actually just going to read a little bit and synthesize what he said. But I asked Kurt y'all's question, maybe my question too, about when there's a Rayleigh scattering event, is there absorption for that 10 to the minus 13th second? Why wouldn't we call that absorption? The energy seems to be absorbed for a 10 to the minus 13th of a second and then re-emitted. And here's what Kurt says. He says, you can think about this in various ways, each of which is a conceptual or mathematical model that probably doesn't really correspond to what real photons do. One is that the electric field of the incoming light causes electrons to scatter, and the scattering atom to oscillate at the same frequency as the incoming light. This is sort of the mental model we've been discussing today. So those accelerated oscillating charges radiate. The outgoing radiation is seen as scattered light. And this is sort of the classic Maxwell's equation interpretation of me. No absorption is required in this mental model. Kurt goes on to say, what happens for a single photon viewed as an elementary particle scattering in a new direction is much harder to visualize. Is it absorbed for a moment and re-emitted in a new direction? That's certainly the way it's described by Feynman in quantum electrodynamics. However, I don't think anyone has a true understanding of what really happens in a way that can be visualized by humans, even though the math of QED is correct in all cases. But then he goes on to say, I think the relevant point for us is that from a practical standpoint for ocean optics, the process of absorption shows up in a measurement only if the photon is absorbed and stays absorbed. If a photon is absorbed and re-emitted in 10 to the minus 13 seconds, it's the same as instantaneous scattering. Our laboratory measurements are not differentiating that. And then this last note was, as Feynman often said, no one knows what a photon is, and it's best not to think about it. He says it's nobody's business what it does during a scattering event. And I think the same holds true for what really happens in a single photon, single electron scattering process. Those spatial and temporal processes are really challenging. So I think both yes to the many interpretations we discussed, but also, I want to reemphasize that a lot of this are mental models that help us to make our measurements and help us to move forward. But there is sort of a deeper fundamental weirdness that is there to be explored. And I really do recommend QED by Feynman. That's, it's a short read, although extremely weird, and it's fun. Okay, from there, I'll say thank you and see you to Andrew.